now we have an understanding of the electrical activity, how it moves through the chambers, how it moves through the heart. What we're going to talk about now is how the autorhythmic cells actually spontaneously depolarize. How do these cells on their own just fire an action potential? How are they autorhythmic? Okay, so we know that they have the ability to spontaneously depolarize, and this goes back to knowledge that we should have from the beginning of the semester. We know that if a cell has permeability to an ion, like let's say there's permeability to a specific ion, the membrane potential will then fluctuate. The membrane potential will then approach the equilibrium potential of that ion. Okay, so if we have a cell and we increase the permeability to sodium, the membrane potential will start approaching the equilibrium potential of sodium. So that is to say, if we increase the permeability of sodium or chloride, we're going to increase the membrane potential. The membrane potential will become more positive. We're going to approach depolarization. We're going to approach action potential. If we increase the permeability to potassium, we're going to decrease the membrane permeability. We're going to decrease the membrane potential. Remember, the membrane potential for potassium, or the equilibrium potential for potassium rather, is very negative. So if we open up lots of potassium channels, the membrane potential becomes negative, and that is how we spontaneously depolarize and repolarize these cardiac cells. Okay, so the first thing we'll talk about is the ionic basis of a pacemaker cell, and then we'll look at the ionic basis of a contractile cell. I want you to keep those two types of cells very distinct, very different. Right? So let's draw this out here. So we're going to talk about the ionic basis of a pacemaker. All right, so the ionic basis of the electrical activity for a pacemaker cell. This is specific to a pacemaker cell. Okay, I'm going to keep saying that because some students tend to confuse these two types of cells. We have pacemaker cells, we have contractile cells, right? So we have our membrane potential here. And we've got time. Now we know that threshold is about -50 here. And then resting is going to be about -70. So this is resting, the resting membrane potential. And then we have threshold at -50. 70. Okay, so there are 4 phases that describe the ionic movement of this cell. Okay. Okay, so let's describe these 4 phases here. So we got 1, 2, 3, and 4. Okay. Now the first thing that happens here is we have closing of potassium channels. All right, so the membrane is at rest to start. It's at -70. And what's happening here is that potassium channels were open. So the first thing we have is that the membrane permeability to potassium is going to decrease. Okay. So there's a decrease in the membrane permeability here. And then we also have the opening of what we call funny channels, which is going to allow the movement of sodium and potassium, or sodium rather. Okay. So we have the closing of the membrane channels for potassium and the opening of some sodium channels, which we call funny channels. So I'm going to put in brackets here, funny. Okay. And that allows the membrane to begin depolarizing. So we can see that happening here. That initial upstroke is going to be where the membrane leaves rest, so it starts approaching the membrane, the equilibrium potential of sodium, which is positive. So it's going to start depolarizing and start becoming more positive. This is going to trigger the opening of calcium channels, but these are slow calcium channels. Okay? So at this point, we're going to have closing of those funny channels and opening of calcium channels, slow calcium channels. So we're going to decrease the membrane permeability to sodium and increase the membrane permeability to calcium. Okay. And in doing so, we're going to even further depolarize this cell. Right now, we open up some more calcium channels, but they're slower. So they're not going to rapidly depolarize the membrane just yet. Step 3 is where we rapidly depolarize the membrane, and this is the opening of fast potassium channels. Fast calcium channels, I'm sorry guys. Fast calcium channels. So this is where we further increase the membrane permeability to calcium. And that is the upstroke. This is going to rapidly increase, and that is going to rapidly depolarize the cell. And this is where we fire an action potential. So action potential here. This is about +30 here, which is very positive. So the membrane permeability rapidly approaches the equilibrium potential of sodium, which is very positive. Now, after we fire this action potential, then we have the reverse of those channels. Potassium channels are now open, and calcium channels will close. So the final phase here is the opening of potassium channels and closing of those fast calcium channels. So we have the decrease of the membrane permeability to potassium, to calcium, and then an increase in the membrane's permeability to potassium. Okay. Let's highlight these important ones. Okay. So this is how a pacemaker cell fires an action potential in the absence of external stimulus, in the absence of any neuronal input. A pacemaker cell can spontaneously depolarize and fire an action potential by changing the amount of channels in the membrane, by changing the permeability of the membrane to certain ions. Any questions here? Okay, so just to review that here, we have the spontaneous depolarization brought about by sodium and potassium channels. The first thing that happens is those potassium channels close. When those potassium channels close, we still have the movement of sodium using funny channels. All right, so the membrane begins to depolarize because now sodium is coming in. Okay, that depolarization, that initial upstroke from sodium, is going to trigger the opening of calcium channels. But these are slow calcium channels at first. And so the initial depolarization happens because of sodium via funny channels and because of calcium via slow calcium channels. The upstroke, the rapid upstroke, or the rapid depolarization of the cell to threshold, right, happens because of the opening of fast calcium channels. So when these faster calcium channels open, you rapidly polarize the membrane, you fire an action potential. And then finally, the membrane completely repolarizes by opening potassium channels and closing those fast calcium channels.